Have you ever wondered why the universe appears the same everywhere we look? It's a question that has puzzled scientists for decades. No matter where we turn our telescopes, the cosmos appears remarkably uniform. But why should this be the case? The mystery of the universe's uniformity is a profound one. Historically, scientists have grappled with this conundrum, searching for an explanation that fits within our understanding of physics and cosmology. Our early theories were challenged by this cosmic uniformity, leading us to question our basic assumptions about the universe's structure and origins. Enter cosmic inflation. This theory, proposed in the late 20th century, offers a compelling explanation for the universe's uniform appearance. Cosmic inflation suggests that the universe underwent a brief but extremely rapid expansion shortly after the Big Bang. This rapid expansion, or inflation, stretched the universe far beyond its original size. But what motivated the introduction of cosmic inflation? The theory was proposed to address several key issues within the standard Big Bang theory. These issues, known as the horizon problem and the flatness problem, revolve around the uniformity of the universe and the precise balance of its geometry. The horizon problem refers to the puzzle of why distant parts of the universe, which have never been in contact, have the same temperature. The flatness problem, on the other hand, questions why the universe's density is so finely balanced that it appears flat on large scales. Cosmic inflation provides a compelling solution to these problems. By proposing a period of rapid expansion in the early universe, it explains why the universe appears so uniform and why it has the geometry it does. It also introduces fascinating concepts like quantum fluctuations and the inflationary epoch, which we'll explore in more detail later. So, to understand the mystery of the universe's uniformity, we must delve into the world of cosmic inflation. As we journey through this cosmic theory, we'll unravel the details of how it explains the universe's uniformity and the evidence supporting it. Cosmic inflation is a concept that might just hold the answer to our question. It's a theory that takes us back to the earliest moments of the universe, to a time when everything we see around us was compressed into a space much smaller than a single atom. At this point, something extraordinary happened. The universe began to expand, not at a slow and steady pace, but at an incredibly rapid rate. It inflated, much like a balloon being blown up, but on a scale that's hard to even comprehend. This period of rapid expansion is what we refer to as cosmic inflation. In the blink of an eye, the universe grew from the size of a subatomic particle to something closer to the size of a grapefruit. This was an expansion far greater and faster than anything we can observe in the universe today. But why did this happen? Why did the universe inflate in this way? Well, the answer to that lies in the very laws of physics themselves. You see, in the early universe, the forces of nature as we know them today were not separate entities. They were all part of a single unified force. As the universe cooled following the Big Bang, these forces began to separate out, and as they did, they released a huge amount of energy. This energy is what drove the rapid expansion of the universe, causing it to inflate. Cosmic inflation isn't just an idea that sprang out of nowhere. It was proposed to answer some very specific questions about the universe. For instance, why is the universe so uniform on large scales? Why does it appear the same in all directions? And why does it seem to be flat rather than curved? These are questions that the original Big Bang theory struggled to answer. But cosmic inflation provides an elegant solution. By expanding the universe so rapidly, it ironed out any irregularities and created the uniform, flat universe we see today. This theory emerged out of necessity, aiming to solve certain problems with the Big Bang theory. The proposal of cosmic inflation came with specific motivations. Picture the early universe as a cauldron of chaos, a roiling soup of particles and forces. But here's the thing, the Big Bang theory, while groundbreaking, had its limitations. It couldn't explain certain puzzling aspects of the universe, such as why it appears so homogeneous and isotropic, meaning it looks the same from every direction. Enter cosmic inflation, a theory proposed to iron out these wrinkles in our understanding. It postulates a period of extremely rapid expansion in the universe's infancy, smoothing out any irregularities and creating the uniformity we observe today. Moreover, it addresses the horizon problem, the mystery of why distant regions of the universe, which have never been in contact, have the same temperature. A key figure in this proposal was physicist Alan Guth. Alan Guth, a physicist, played a significant role in the development of the inflationary theory. Goethe in the late 20th century was grappling with the fundamental questions about the early universe that the Big Bang theory couldn't quite answer. Goethe proposed the idea of cosmic inflation, a brief period of exponential expansion in the universe's infancy. His revolutionary concept provided solutions to some of the most puzzling cosmological conundrums, including the flatness problem and the horizon problem. Goethe's work didn't stop there. Alongside Stephen Hawking and Katsuichi Sato, he developed the Guth-Hawking-Sato theorem. This theorem further refined the understanding of the early universe, detailing the conditions necessary for inflation to occur. Goethe's theory explains an epoch in the universe's timeline, known as the Inflationary Epoch. This period of rapid expansion set the stage for the universe as we know it today, shaping its large-scale structure and uniformity. The Inflationary Epoch was a defining period in the universe's timeline. Picture this: a time when the universe was only a fraction of a second old, yet experienced an incredibly rapid expansion that propelled it from a size smaller than an atom to a vast expanse. This was no ordinary growth spurt. We're talking a rate so fast it's like a grape instantly inflating to the size of the Earth. This period, known as the Inflationary Epoch, is key to understanding the shape and structure of our universe. During this brief moment in cosmic history, the universe expanded faster than the speed of light. Yes, you heard it right, faster than light. And here's the kicker. This rapid expansion smoothed out the universe, ironing out any wrinkles and irregularities, creating the uniform and isotropic universe we see today. This epoch was instrumental in creating the uniformity and isotropy we observe in the universe today. Quantum fluctuations played a crucial role during the inflationary period. Now you might wonder, what exactly are these quantum fluctuations? Simply put, they're temporary changes in energy that occur in empty space due to the uncertainty principle of quantum mechanics. Think of it like the universe at its most microscopic level, constantly buzzing with energy, even when it seems like nothing's happening. But how did these fluctuations contribute to the formation of cosmic structures? Well, during the inflationary period, these tiny fluctuations were stretched to cosmic proportions. This created slight variations in density throughout the universe. Over billions of years, areas of higher density attracted more matter, eventually forming the galaxies and galaxy clusters we observe today. In essence, these quantum fluctuations served as the seeds for all the cosmic structures in the universe. These fluctuations also help address the horizon problem, but we'll delve deeper into that in our next scene. The horizon and flatness problems are two significant issues in cosmology. These seemingly complex issues are, in essence, about the uniformity of our universe and its peculiar geometry. The horizon problem revolves around the uniform temperature of the cosmic microwave background radiation. This radiation is a snapshot of the universe when it was just a baby, only a few 100,000 years old. But here's the catch. Distant regions of the universe, separated by vast cosmic distances, have the same temperature to an astonishing degree. The problem is, according to the classic Big Bang theory, these regions could not have exchanged heat or any information due to their vast separation. This is what we call the horizon problem. On the other hand, the flatness problem concerns the geometry of space. General relativity tells us that the shape of space is determined by its density. If the density is just right, space is flat. But it would have to be incredibly fine-tuned in the early universe to be as close to flat as we observe today. This is known as the flatness problem. Now let's bring in cosmic inflation. It provides elegant solutions to both these problems. Inflation proposes that in the very early universe, a tiny fraction of a second after the Big Bang, the universe underwent a rapid expansion. This expansion was so fast and so vast that those distant regions we talked about earlier were actually close together before inflation. They were in causal contact, allowing them to reach the same temperature. This solves the horizon problem. As for the flatness problem, inflation stretched space to such an extent that it appears flat, just like the surface of a balloon seems flat when you're on it. This rapid stretching ironed out any initial curvature, leaving us with the flat universe we observe today. After this rapid inflation, the universe transitioned into the hot Big Bang phase. There's a wealth of observational evidence supporting the inflationary theory. We see this evidence in the cosmic microwave background, or CMB, which is the afterglow of the Big Bang. By examining minute variations in the CMB's temperature, astrophysicists have found patterns consistent with the idea of a rapid, early period of inflation. One of the key features observed in the CMB is its uniformity. The temperature of the CMB is remarkably consistent across the sky, with only tiny variations. This uniformity is difficult to explain without invoking some mechanism like inflation to smooth out any larger differences. Moreover, the CMB is not perfectly uniform. It contains slight ripples or fluctuations. These fluctuations are believed to be the seeds of all existing cosmic structures, including galaxies and galaxy clusters. The statistical properties of these fluctuations, particularly their scale invariance, are in excellent agreement with the predictions of inflation. Besides the CMB, the large-scale structure of the universe also provides strong evidence for inflation. The distribution of galaxies and galaxy clusters across the universe is highly uniform, just as inflation predicts. However, we should also mention the BICEP-2 experiment, a South Pole-based project that in 2014 claimed to have detected gravitational waves from the Inflationary Epoch. These waves would be a direct imprint of inflation, and their discovery was initially hailed as definitive proof. Unfortunately, it later turned out that the signal BICEP-2 detected could be fully explained by dust within our own galaxy. This serves as a reminder that while we have strong evidence for inflation, definitive proof is still elusive. Despite this, inflation remains the leading explanation for the observed properties of the universe. It provides a mechanism for generating the initial perturbations that grew into galaxies, explains the large-scale uniformity of the universe, and predicts a nearly flat geometry for the universe, which is what we observe. These observations and experiments continue to test inflationary predictions. As technology advances and our ability to observe the universe improves, we'll continue to refine our understanding of the inflationary epoch and its role in the formation of the universe as we know it. Like any scientific theory, cosmic inflation has its critics and alternative theories. Indeed, no theory is without its detractors, and cosmic inflation is no exception. Some critics argue that inflation is not predictive or testable, a key criterion for scientific theories. Others propose alternative theories like the cyclic universe model, which posits that the universe undergoes endless cycles of expansion and contraction, or the string theory landscape, which suggests there are an astronomical number of possible universes within a larger multiverse. There are also those who challenge the idea of a single inflationary event, proposing instead a chaotic inflation model where inflation occurs at different times and places in the universe. Furthermore, some critics argue that the inflationary theory is too flexible, accommodating a wide range of observations. Despite these, cosmic inflation remains a compelling explanation for the uniformity of the universe. It continues to be a crucial part of our understanding of the cosmos and its origins. So, what have we learned about our universe today? Well, we've embarked on a journey from the initial spark of cosmic inflation to its profound implications on our understanding of the universe. We've grappled with the mysteries of why the universe appears the same everywhere, and how the theory of cosmic inflation offers a compelling explanation. We've learned about the significant role of Alan Guth in developing the inflationary theory, and how it proposed a period of rapid expansion in the early universe. This inflationary epoch, as it's called, was a time when the universe grew exponentially, smoothing out any irregularities and creating a uniform, isotropic universe. We've also delved into the role of quantum fluctuations during this inflationary period. These tiny fluctuations, magnified by inflation, are thought to have led to the formation of the large-scale structures we see in the universe today. Then, we tackled the horizon and flatness problems. These conundrums, which pose challenges to the traditional Big Bang theory, find resolution in the concept of cosmic inflation. By stretching space exponentially, inflation ensures the uniform temperature across the cosmic microwave background and the fine-tuning required for a flat universe. We further explored the end of inflation, transitioning into the hot Big Bang phase through a process known as reheating. This was a time when energy got released, setting the stage for the universe as we know it. We haven't shied away from the controversies either. We touched on the BICEP-2 experiment and the cautionary tale it provides. But we also highlighted the wealth of observational evidence that supports the inflationary theory, from the cosmic microwave background to large-scale structure studies. Finally, we acknowledged that while cosmic inflation is a compelling theory, it's not without its critics and alternative theories. The beauty of science is in its constant evolution, in our relentless quest for understanding. And that, my friends, is how cosmic inflation has shaped our understanding of the universe.